Hey, grade 11s. Today we're going to talk about the kinetic molecular theory and use it to explain gases. So kinetic molecular theory, the word kinetic means motion, and molecular obviously meaning molecules. So we're talking about the motion of molecules to explain gases. And all of the properties of gases and solids and liquids we can explain using the KMT. That's a short form for kinetic molecular theory. The theory basically is used to explain gases, but we're going to later on use it to also explain the properties of solids and liquids. So some of the properties of gases are that they have mass, they're compressible, they fill their container completely, they move through each other easily, in other words, they diffuse, and they exert pressure on the container, and the pressure also depends on temperature. So we can go through all of these 6 properties and talk about them and explain them using the motion of particles and kind of just some logic of an understanding of the world around us. So these properties have all been explained by something called the kinetic molecular theory, or KMT for short. So our kinetic molecular theory of gases. The first thing we said was that gases are made of very small particles that have mass. Compare them, in order to figure this out or to prove this, we can take the mass of a basketball, or any ball for that matter, and weigh it when it has air and weigh it when it doesn't have air. Even a tire and a rim, if you just weigh them separately, no air stuck inside, but if you weigh them together, it should gain a little bit of mass. So air does have mass. The other thing we can show or prove that gas particles are very far apart. And the reason why we can say that is because we can actually compress those gases. We must be able to be pushing them back together, pushing them closer together. The particles of gas are so far apart that their size of the particles is negligible, which means that they really are insignificant. The space between them is huge, and the particles themselves are tiny. Gas particles are also rapid, random motion, and they're constantly moving. And they have a lot more motion than their solid and liquid counterparts. So this is what causes collisions between particles in a container, and that actually what causes pressure. So if you think of what's going on inside of a balloon or a tire, the particles, the gas molecules are moving around, and they're hitting the walls of the container, and they're pushing out. Now, if they're hitting the walls of the container with a constant amount of energy, that will maintain that container's shape. So that's why a balloon will maintain its shape. But if we hit the wall of the container and we gain energy or we lose energy, then we'll either speed up or slow down. The speed of the particles is actually what tells us the amount of energy or amount of temperature. So if you go into hitting the wall of the container with a certain amount of energy and you come off with less energy, in other words, E1 is greater than E2, your pressure would drop because the particles are giving off energy. So that's like putting a balloon into a freezer. The gas particles hit the side of the balloon, they'll lose energy to the freezer, to the surroundings, and they come off slower. And the next time they hit the wall of the balloon, they are actually moving more slowly, so they're not hitting it as hard, so the pressure is starting to drop. If you have the opposite, so you put the balloon in like in the window where it's sunny and hot, the particles are going to hit the wall of the balloon, they're going to pick up some of that energy, and they're going to ricochet off the wall of the balloon with more energy than they hit it with, and they're going to push harder the next time they hit. So the pressure would rise. So this is why if you heat it up, the pressure rises. Now, if you keep the temperature constant, the particles are just hitting the wall of the container. They're not gaining or losing energy, so their motion, their speed stays the same, and the pressure doesn't change. Now, the other thing we should talk about is collisions. So in the real world, anytime you have things collide, you have friction, and you have a loss of energy. With gas particles, we assume that those collisions are perfectly elastic. So if I drop a ball from a certain height, the ball will never bounce back to that same height because some energy gets lost in that collision. But with gases, the collisions are perfectly elastic. So that's what allows pressure to remain constant when you have constant temperature, so those elastic collisions. An inelastic collision would look like that, where the ball is not bouncing as high. Now, to one of our favorite things in chemistry and science is something called the Maxwell-Boltzmann curve. The average energy of gas particles depends only on temperature. So in other words, the speed of the molecules is temperature dependent. The higher the temperature, the higher the energy of the gas particles. Now, since mass is constant, velocity of the particles must increase with temperature. So if you've taken physics, you may have seen this equation. KE, kinetic energy, is 1/2 mv squared. So since mass is constant, the energy is completely proportional to the velocity. So in other words, if we speed up molecules, the kinetic energy of them increases. And we can show this using a Maxwell-Boltzmann distribution. So if you think about the energy in your bedroom, in your classroom, in the kitchen, whatever, if the temperature is 20 degrees Celsius, that means that's the average of all of the molecules. Some of the air molecules and molecules in room are colder, some are hotter, but that's an average. Just like if I said the class average in chemistry is 70%, that would mean that half the class is higher, half the class is lower. That's an average. So that's what this distribution shows us. And if we heat up those particles, then the average is increasing. So an example I like to use is just talking about taking the final exam. If to pass the exam, you need a 50%. If I gave students the exam at the first day of class, I'm going to bet that the class would not do so well, so maybe the average would be pretty low. The most students would be down here somewhere. Some students might actually pass the exam. They might get over a 50. Maybe they've taken chemistry before, or they just really like this stuff. But most students probably not going to pass the exam without having taken the course. So let's say our average on the exam was like 30%. But now as we put more time into the course, more and more students are going to be able to pass. So you're going to see that curve start to shift, which is what the blue curve is representing. So if you look at the blue curve, more of the particles are past the 50% line. So that would be like if we took the exam maybe now, halfway through the course, more of our students would be able to pass. And as we put more and more energy into the course, more and more students will be able to pass the exam. And that's true of particles. So if we're talking about water, we heat up water, it starts at, let's say, instead of 30%, let's say it starts at 30 degrees. As I heat it up and heat it up, heat it up, more and more molecules are going to have more and more energy. So we might be at 60 degrees here. And that's our average. There's still slower molecules, there's still faster molecules, but on average, the molecules, the average energy has increased. And then the last one is gas particles exert no forces. Now again, I shouldn't say no forces because the forces are still there, but the particles are moving so fast that the forces have been overcome. An example of this is a magnet. If you throw a magnet or have a magnet it's moving slowly near a piece of metal, it'll attract. But if you have that magnet and you throw it really fast past the piece of metal, it probably won't stick because the motion, that speed, that momentum of that magnet is overcoming the force between the magnet and the piece of metal. So there's our introduction to the kinetic molecular theory.